Imagine spending months building an advanced machine learning model, only to watch it fail because of one hidden problem. It wasn't the algorithm, it wasn't the code, it was the data. This single mistake causes countless AWS machine learning specialty exam questions to trip up candidates, and it costs real companies millions of dollars in wasted time and poor decisions. If you truly want to pass the AWS Certified Machine Learning Specialty, MLA C01, exam and understand how machine learning works in the real world, this is one section you cannot afford to skip. Welcome to Section 1 of your AWS Certified Machine Learning Specialty, MLA C01, prep course. In this lesson, we're exploring one of the most important foundations of machine learning, data engineering. You'll learn how data is collected, stored, cleaned, transformed, and prepared before it ever reaches a machine learning model. These concepts appear throughout the certification exam because AWS expects you to understand that great machine learning always begins with high-quality data. As we move through this section, I'll explain each concept in simple, practical language with real-world examples that make even complex AWS services easier to understand. If you're joining us here for the first time, I highly recommend watching the previous lessons first, since each section builds on the knowledge you've already learned and will make the rest of the course much easier to follow. Don't forget to download the free study PDF linked in the description. It's a great companion for reviewing the key concepts after the lesson and reinforcing what you've learned. Now, grab your notes, stay focused, and let's begin building the strong data engineering foundation that every successful AWS machine learning professional needs. The very first step in any machine learning pipeline is data ingestion, which simply means bringing your raw data into the AWS cloud. Data can come from many different sources, such as customer databases, live application logs, or even smart devices connected to the internet. Your job as a machine learning specialist is to choose the right AWS tool to move this data safely and efficiently. If your data arrives in slow, predictable batches, you will use completely different services than if it streams in constantly every single second. Understanding the speed and volume of your incoming data is a critical concept tested frequently on the certification exam. When dealing with streaming data, which is data that flows continuously like a river, Amazon Kinesis is your absolute best friend. Kinesis data streams allows you to capture gigabytes of data per second from hundreds of thousands of sources in real time. This is perfect for scenarios like tracking live website clicks or monitoring financial transactions for immediate fraud detection. On the exam, anytime you see keywords like real-time, streaming, or continuous data, your mind should immediately jump to Amazon Kinesis. It is a fundamental service that acts as the front door for high-speed data entering your AWS environment. Sometimes, you need to save that incoming streaming data directly into a storage system for future analysis, and this is where Amazon Kinesis Data Firehose comes into play. Unlike Kinesis data streams, which requires you to write custom code to process the data, Firehose is fully managed and automatically delivers data to destinations like Amazon S3. It can even compress and encrypt the data before saving it, which saves you money and keeps your information highly secure. If an exam question asks for the easiest way to load streaming data into an AWS storage service with zero administration, Kinesis Data Firehose is almost always the correct answer. For batch data ingestion, where you move large chunks of historical data all at once, AWS offers services like AWS DataSync and the AWS Snow family. DataSync is wonderful for quickly moving terabytes of data over the internet from your local office servers straight into AWS storage. However, if your internet connection is extremely slow or you have massive petabytes of data, it could take months to transfer everything online. In those extreme cases, AWS will literally mail you a physical hard drive called the Snowball, which you plug into your own servers, load up with data, and safely mail back to Amazon. The exam will test your ability to recognize when the internet is too slow and a physical Snowball device is required. Once your data successfully arrives in the AWS cloud, you need a secure and highly scalable place to store it. Amazon's simple storage service, commonly known as Amazon S3, is the central foundation of almost every single machine learning architecture on AWS. S3 is an object storage service, meaning it stores your files exactly as they are, whether they're images, text documents, or giant database backups. It is designed to be incredibly durable, so the chances of ever losing a file are practically zero. S3 acts as your central data lake, which is a massive pool where all your raw data waits securely until you are ready to analyze it. A major advantage of using Amazon S3 for your machine learning data lake is its intelligent tiering and cost management features. Not all data is used every single day, so keeping older, rarely used files in standard storage can become very expensive over time. S3 allows you to automatically move older data into cheaper storage classes, like S3 Glacier, which is designed for long-term archiving. Knowing how to balance data accessibility with storage costs is a key skill for real-world jobs and a common scenario presented in exam questions. You must always ensure your active training data is immediately available while archiving historical data efficiently to save money. After storing your raw data in Amazon S3, you will often find that it is quite messy and not yet ready for machine learning. Data transformation is the necessary process of cleaning, formatting, and combining your raw files into a neat, highly usable format. For example, you might need to combine a file containing customer names with a separate file containing their actual purchase history. This process of extracting, transforming, and loading data is universally known as ETL. AWS provides several powerful tools to handle ETL processes, and knowing which one to choose is heavily tested on the machine learning specialty exam. AWS Glue is a fully managed ETL service that makes it incredibly simple to clean and organize your data. Because it is completely serverless, you do not have to worry about setting up or managing any underlying computer servers, which allows you to focus purely on your data. AWS Glue can automatically crawl through your S3 buckets, discover what kind of data you have, and create a central dictionary called the Glue Data Catalog. This catalog acts like a digital index in a library, making it extremely easy for other AWS services to find and understand your datasets. Whenever an exam question mentions a serverless ETL data catalog, AWS Glue is the intended target. Under the hood, AWS Glue actually runs on Apache Spark, which is an open-source framework designed to process massive amounts of data very quickly. Spark distributes the heavy lifting across multiple computers working together, making it perfect for transforming gigabytes or terabytes of information in record time. You can write your own Spark code in Python or Scala, or you can use Glue Studio, a visual interface that lets you build data transformation workflows without writing any code at all. Understanding that AWS Glue utilizes Apache Spark is important, as the exam often tests your knowledge of the underlying technologies that power these managed AWS services. Another fantastic tool for heavy data transformation is Amazon EMR, which stands for Elastic MapReduce. While AWS Glue is completely serverless and hands-off, Amazon EMR gives you total administrative control over the cluster of servers processing your data. It is widely used by enterprise companies that already have complex, custom big data applications running on frameworks like Apache Hadoop or Apache Spark. If an exam scenario describes a company that wants to migrate their existing, highly customized Hadoop cluster to the cloud and maintain deep configuration control, Amazon EMR is the preferred choice over AWS Glue. Sometimes you just need to do a quick, simple transformation on data exactly as it streams into your system. For this, you can easily use AWS Lambda, a powerful service that lets you run small pieces of code automatically in response to events without managing any servers. A common exam scenario involves incoming data arriving in Kinesis data firehose that needs a quick format change before being saved to Amazon S3. You can configure firehose to trigger a Lambda function, which intercepts the data, cleans it up, and passes it right back to firehose for final delivery. This is a brilliant, highly cost-effective way to perform lightweight data engineering on the fly. Let us talk about data formats, because how you save your data inside Amazon S3 heavily impacts the speed and cost of your machine learning pipelines. Storing data as simple text files, like CSVs, is easy for humans to read but very slow and expensive for computers to process. Instead, you should always convert your large datasets into optimized, columnar formats like Apache Parquet or Apache Orc. These specific formats compress the data tightly and allow analytical tools to skip irrelevant columns, drastically speeding up read times. The AWS exam will frequently ask how to improve read performance or reduce query costs, and converting CSV files to Parquet is a classic, highly rewarded solution. Another critical AWS service for data engineering is AWS Step Functions, which helps you coordinate multiple AWS services into seamless, fully automated workflows. Building a machine learning pipeline often involves many separate steps, such as triggering an AWS glue job, waiting patiently for it to finish, and then launching a model training process. Step functions allows you to stitch these individual tasks together using a visual state machine. If an error occurs during the ETL process, step functions can automatically retry the task or send a quick alert to your engineering team. Recognizing step functions as the premier orchestration tool for complex data workflows is essential for passing the exam. Security is always priority number one on AWS, and data engineering is absolutely no exception. As you move data through Kinesis, transform it with Glue, and store it in S3, you must ensure it remains completely safe from unauthorized access. You will heavily use AWS Identity and Access Management, or IAM, to give each service exactly the permissions it needs and nothing more. For example, your AWS Glue job needs an IAM role that explicitly allows it to read data from your specific S3 bucket. The exam will definitely try to trick you with overly broad security permissions, so always remember the principle of least privilege when designing data pipelines. You must also protect the actual contents of your data using encryption, both when the data is traveling over the network and when it is resting safely in storage. AWS Key Management Service, or KMS, is the central hub for creating and controlling the cryptographic keys that lock and unlock your digital data. You can easily configure Amazon S3 and Amazon Kinesis to automatically encrypt your information using these secure KMS keys. If an exam question asks how to meet strict compliance rules for protecting sensitive patient or financial records, enabling encryption at rest with AWS KMS is absolutely mandatory. To keep accurate track of what is happening inside your data pipelines, you will rely heavily on Amazon CloudWatch, the primary monitoring and logging service on AWS. Every time a Glue job runs or a Lambda function executes, they send detailed logs and performance metrics straight to CloudWatch. This allows you to easily set up automated alarms that notify you immediately if a data ingestion stream fails or an ETL job takes unusually long to complete. Knowing how to troubleshoot broken data pipelines using CloudWatch logs is a very practical skill that is regularly tested through troubleshooting scenarios on the machine learning specialty exam. An emerging and highly useful tool for data engineers preparing for machine learning is Amazon SageMaker Data Wrangler. While AWS Glue is a general-purpose ETL tool, Data Wrangler is specifically built into the SageMaker environment to help data scientists visually prepare data for modeling. It allows you to quickly connect to S3 or Athena, clean up messy columns, and apply built-in data transformations with just a few simple clicks. It beautifully bridges the gap between raw data engineering and data science, making it a very popular topic on the newly updated versions of the AWS machine learning exam. As we wrap up this technical content, remember that a strong data engineering foundation makes everything else in machine learning significantly easier. If you correctly design your Kinesis streams for real-time ingestion, transform your data cleanly with AWS Glue, and store it efficiently in S3 using Parquet formats, your models will train faster and cost much less money. The exam tests not just your knowledge of individual services, but your clear ability to connect them together into a logical, highly efficient architecture. Always think logically about how data flows from the outside world, gets thoroughly cleaned, and securely rests in the central data lake. Congratulations on completing Section 1 and taking this massive first step toward your AWS Certified Machine Learning Specialty certification. To ensure these critical data engineering concepts stick firmly in your mind, I highly encourage you to complete the attached practice test right now. Practice questions significantly improve your long-term retention and expose you to the exact wording you will face on the real exam. This carefully crafted practice test is included with this lesson, so please take full advantage of this active learning opportunity. Great job so far, and I will see you in the next section where we will dive into exploratory data analysis and feature engineering. Welcome back to Section 2 of our AWS Certified Machine Learning Specialty course, where we explore the fascinating world of exploratory data analysis and feature engineering. In this lesson, you will learn how to deeply understand your data and transform it into the perfect format for your machine learning algorithms. This topic is absolutely vital because the quality of your input data completely determines the intelligence of your final model. I am incredibly excited to show you these powerful techniques, as they are the exact skills real data scientists use every single day to unlock hidden insights. Take a deep breath, get ready to dive into the data, and let us prepare you for success. Exploratory data analysis, often called EDA, is the crucial process of investigating your dataset before you even think about building a predictive model. Imagine trying to build a house without first looking at the land and understanding the soil. EDA allows you to look closely at your data to find hidden patterns, spot obvious errors, and understand the general relationships between different variables. On the certification exam, you will frequently be asked to identify the best tool for this job, and using Amazon Athena to quickly query your raw data using standard SQL is a very common and highly recommended approach. When you begin exploring a new dataset, your first step is usually to calculate basic descriptive statistics. This means finding the average value, the middle value known as the median, and understanding how spread out your numbers are using variance. These simple numbers instantly give you a mental picture of what your data looks like and help you spot immediate problems. For example, if the average age in your customer database is surprisingly high, but the median age is low, you immediately know your data is heavily skewed by a few unusually old customers. Reading long tables of numbers can be exhausting, which is why data visualization is a massive part of exploratory data analysis. Creating visual charts makes it incredibly easy for the human brain to instantly recognize complex trends and hidden anomalies. You can create scatter plots to see if two variables move together, or use histograms to see the overall distribution of a single category. For the exam, remember that Amazon QuickSight is the premier AWS service for building interactive visual dashboards that can help business leaders understand these data patterns without writing any code. As you explore real-world data, you will quickly discover that it is rarely perfect, and missing values are one of the most common problems you will face. A customer might forget to fill out their age on a form, leaving a completely blank space in your database. You cannot simply feed blank spaces into a mathematical model, so you must decide how to handle these missing data points. A very common exam question will test your knowledge of when to completely drop a row with missing data versus when to logically guess the missing value, a process formerly known as data imputation. Data imputation involves filling in those blank spaces with logical, mathematically calculated guesses. The simplest method is mean imputation, where you just calculate the average of all the other rows and use that number to fill the blank spot. However, if your data has massive outliers, replacing missing values with the median is actually a much safer choice because the median is not affected by extreme high or low numbers. The exam will heavily test your ability to recognize when a simple mean imputation might ruin your dataset and when a median imputation is the smarter choice. Another massive challenge you will face during data exploration is dealing with outliers, which are weird data points that sit far outside the normal range. Imagine a database of normal house prices where one mansion is accidentally listed for $1 billion. This massive outlier will violently pull your mathematical model in the wrong direction, causing it to make terrible predictions for normal houses. Data scientists frequently use a statistical technique called the interquartile range to mathematically identify these outliers so they can be safely removed or adjusted before the training phase begins. To make the entire process of finding missing values and outliers much easier, AWS provides a visual tool called Amazon SageMaker Data Wrangler. Data Wrangler creates a beautifully clear data quality report with just a single click, instantly highlighting all your missing information and extreme anomalies. Instead of writing hundreds of lines of Python code to clean your dataset, you can simply click through visual menus to drop columns, fill in blanks, and filter out outliers. Recognizing Data Wrangler as the fastest visual tool for rapid data cleaning is a guaranteed way to score easy points on the exam. Once your data is clean and fully explored, you must move on to feature engineering, which is the true secret weapon of successful machine learning. Feature engineering is the creative process of transforming your raw data columns, which we call features, into new mathematical formats that make it easier for algorithms to learn. For example, a machine learning model might struggle to understand a raw birthdate string, but if you logically engineer that date into a simple age number, the model will suddenly perform much better. The exam heavily tests your ability to choose the exact right mathematical transformation for completely different types of raw data. One of the most important feature engineering techniques is called one-hot encoding, and it is absolutely essential when dealing with categorical data. Machine learning algorithms only understand pure numbers, so if you have a column with text categories like the colors red, green, and blue, the model will be completely confused. One hot encoding solves this by creating a brand new, separate column for every single color, and placing a simple number 1 or 0 in the box to indicate true or false. This is a universally tested concept, so you must always remember to use one hot encoding when converting unrelated text categories into machine learning numbers. However, if your text categories have a natural, logical order, such as the sizes small, medium, and large, you should use a different technique called label encoding. Label encoding simply assigns a sequential number to each category, like a 1 for small, a 2 for medium, and a 3 for large. This carefully preserves the mathematical relationship, allowing the predictive model to clearly understand that large is truly bigger than small. A classic exam trap is applying label encoding to completely unrelated categories like car colors, which accidentally tricks the model into thinking that a blue car is mathematically greater than a red car. Handling large blocks of natural text, like customer reviews or long support emails, requires a special type of feature engineering known as bag of words. This fundamental technique takes a long paragraph and simply counts how many times each individual word appears, turning the unstructured text into a massive table of structured numbers. While this is a decent starting point, it unfortunately gives far too much mathematical importance to common words like the word the, which appear constantly but carry absolutely no real analytical meaning. To quickly fix this common problem, data scientists rely on a highly tested mathematical transformation called TF-IDF. TF-IDF stands for Term Frequency Inverse Document Frequency, and it is arguably the most important text processing concept on the entire certification exam. This brilliant formula heavily rewards unique, highly meaningful words that only appear in a few specific documents, while severely punishing common filler words that appear everywhere. If you are building an automated system to categorize hundreds of legal documents or analyze customer sentiment, TF-IDF is exactly how you turn those written words into powerful numeric features. Whenever an exam scenario asks how to mathematically extract meaningful keywords from raw text, TF-IDF is almost certainly the right answer. Another absolutely critical step in feature engineering is feature scaling, which guarantees all your numbers play nicely together during the training process. Imagine a dataset containing a person's age, which might be 30, and their yearly financial salary, which might be 80,000. Because the salary number is so physically large, the machine learning algorithm will accidentally assume it is completely dominant and a million times more important than the person's age. To fix this dangerous imbalance, we use a technique called normalization to mathematically squeeze all our varying numbers down into a tiny, uniform range perfectly between 0 and 1. A slightly different scaling technique is called standardization, which is highly preferred when your raw data naturally contains extreme statistical outliers. Instead of aggressively squeezing everything into a strict box between 0 and 1, standardization transforms the entire data distribution so it has a perfect average of 0 and a standard deviation of exactly 1. This clever math allows the weird outliers to remain naturally spread out without completely crushing the rest of your normal data into a tiny, unreadable clump. Understanding the subtle mathematical difference between simple normalization and standardization, and exactly when to use each, is a very common troubleshooting scenario you will face on test day. Sometimes you will find yourself with way too many engineered features, perhaps thousands of different columns, which can cause your model to blindly memorize the data instead of actually learning from it. This dangerous problem is known as the curse of dimensionality, and we solve it using a mathematical trick called principal component analysis, widely known as PCA. PCA acts like a digital garbage compactor, carefully squeezing hundreds of related columns down into just a few incredibly powerful columns without losing the original underlying meaning. PCA is one of the most heavily tested mathematical algorithms on the exam, specifically used for reducing the sheer physical size of your dataset. During your initial data exploration, you might encounter a severely imbalanced dataset, which is a massive trap for beginner data scientists and engineers. Think about a credit card fraud detection system, where 99% of the transactions are perfectly normal and only 1% are actually dangerous fraud. If you build a terrible model that simply guesses normal every single time, it will mathematically achieve 99% accuracy, even though it completely failed to find any real fraud at all. The exam will constantly test your ability to instantly recognize when an imbalanced dataset is causing high accuracy scores but delivering terrible real-world performance. To safely fix an imbalanced dataset, you must use a clever mathematical oversampling technique called SMOTE, which stands for Synthetic Minority Oversampling Technique. Instead of just lazily copying the rare fraud examples over and over, SMOTE mathematically generates brand new, entirely fake data points that look incredibly realistic to the algorithm. This perfectly balances the entire dataset, giving the machine learning algorithm plenty of positive and negative examples to study so it can finally learn what a real fraudulent transaction looks like. If an exam question asks how to carefully handle a highly imbalanced dataset without losing critical information, SMOTE is essentially guaranteed to be the right choice. The final step of feature engineering is feature selection, where you bravely delete columns that are simply not helping your model learn anything new. If two columns give the exact same information, like the temperature in Fahrenheit and the temperature in Celsius, keeping both of them only confuses the mathematical algorithm and wastes valuable computing power. You can easily calculate a simple correlation matrix during your exploratory phase to visually see which features are exact mathematical duplicates of one another. By permanently dropping these perfectly correlated features, you dramatically simplify your overall model, reduce expensive training time, and actually improve its final real-world accuracy. Congratulations on successfully completing Section 2 and mastering the critical analytical arts of exploratory data analysis and feature engineering. To truly cement these powerful data transformation techniques into your permanent memory, I strongly encourage you to completely finish the attached practice test right now. Working steadily through realistic practice questions is the single best way to improve your factual retention and prepare for the tricky technical wording of the actual exam. This comprehensive practice test is included heavily with this lesson, so please dive in and aggressively embrace the active learning process. You are doing absolutely fantastic work, and I will see you in the next section where we will finally select our machine learning algorithms. Welcome to Section 3 of our AWS Certified Machine Learning Specialty course, where we finally enter the thrilling phase of modeling and algorithm selection. In this lesson, you will learn how to look at a specific business problem and immediately know which mathematical algorithm is perfectly suited to solve it. This topic is incredibly important because choosing the wrong algorithm is like trying to hammer a nail with a screwdriver. It simply will not work and will cost your company a fortune. I am so excited to guide you through this core machine learning phase, as this is where your data truly begins to think and make intelligent predictions. Get comfortable, prepare to expand your mind, and let us dive into the algorithms. Before we look at specific AWS tools, you must understand the massive, fundamental difference between supervised and unsupervised learning. Supervised learning is used when you perfectly know the answer you are looking for, so you provide the algorithm with historical data that already contains the correct labels. For example, if you want a model to predict house prices, you must train it using a dataset that explicitly includes the final sale prices of previous houses. Unsupervised learning, on the other hand, is used when you have absolutely no labels or correct answers, and you simply want the algorithm to find hidden patterns on its own. Within the world of supervised learning, there are two major subcategories that you will be tested on heavily, known as regression and classification. Regression is the specific mathematical process you use whenever you need to predict a continuous, sliding number, like estimating exactly how much money a customer will spend next year. Classification is completely different, as it is used when you want to sort data into strict, predefined categories, like determining if an email is officially spam or not spam. Knowing immediately whether an exam question is asking for a numerical regression or a categorical classification is the very first step in selecting the correct algorithm. Amazon SageMaker provides a fantastic suite of built-in algorithms that are highly optimized to run incredibly fast on AWS cloud infrastructure. Instead of writing complex mathematical code entirely from scratch, you can simply select one of these built-in algorithms, point it directly at your clean data in Amazon S3, and start training. These built-in options are mathematically tuned to scale perfectly across multiple servers, making them much cheaper and faster than custom code. The certification exam absolutely loves testing your knowledge of these specific built-in algorithms, so we will focus heavily on them throughout this lesson. The most basic but incredibly useful built-in tool is the SageMaker Linear Learner algorithm. Linear Learner is fantastic because it can easily handle both numerical regression problems and categorical classification problems, making it a very versatile tool for your starting baseline. It works by drawing a straight mathematical line through your data to figure out the general trend, which is brilliant for simple tasks like predicting an employee's salary based entirely on their years of experience. You should always consider Linear Learner when you need a fast, highly explainable model before moving on to more complicated algorithms. When you are dealing with standard tabular data, which simply means data organized neatly into rows and columns like a traditional spreadsheet, the XGBoost algorithm is the absolute king. XGBoost stands for Extreme Gradient Boosting, and it works by combining hundreds of simple, weak decision trees together to create one incredibly powerful predictive model. It is famous for winning countless data science competitions and is universally loved for its high accuracy on complex financial or marketing data. If an exam scenario involves maximizing predictive accuracy on a standard spreadsheet of historical customer data, XGBoost is almost always the correct and most powerful answer. Sometimes your business problem involves tracking data that changes constantly over time, like daily weather temperatures or hourly retail store sales. For these specific time series forecasting problems, AWS provides a brilliant deep learning algorithm called DeepAR. Unlike older forecasting methods that only look at one single product at a time, DeepAR can analyze thousands of different products simultaneously to find massive, overarching seasonal trends. Whenever an exam question mentions time series data, forecasting future sales, or predicting supply chain demand based on historical dates, your brain should immediately lock onto the DeepAR algorithm. Now let us shift our focus to computer vision, which is the fascinating field of teaching computers how to see and understand digital images. The SageMaker image classification algorithm is a heavily tested supervised learning tool used to assign a specific category label to an entire picture. For example, if you feed it a photograph of a dog, it will mathematically analyze the pixels and boldly declare that the image belongs in the dog category. It uses complex artificial neural networks under the hood, but SageMaker packages it so beautifully that you do not need a PhD to use it effectively. While image classification looks at the whole picture, the SageMaker object detection algorithm goes a massive step further by finding exactly where specific items are located inside that picture. If you give it a photograph of a busy city street, object detection will mathematically draw tight little boxes around every single car, pedestrian, and traffic light it sees. It not only tells you what is in the image, but it precisely gives you the exact pixel coordinates of where everything lives. You will easily recognize object detection on the exam when a scenario specifically asks to locate, find, or draw bounding boxes around multiple items within a single frame. The most advanced level of computer vision tested on the exam is called semantic segmentation, which requires an incredibly detailed, pixel-by-pixel analysis of an image. Instead of drawing rough boxes around objects, semantic segmentation assigns a strict category label to every single dot of color on the screen, creating a perfectly exact outline of complex shapes. This extreme level of detail is completely mandatory for life or death applications like autonomous self-driving cars, which need to know exactly where the drivable road ends and the dangerous sidewalk begins. If the exam explicitly demands pixel-level accuracy or exact shape outlines, semantic segmentation is your only logical choice. Moving away from images, we enter the world of natural language processing, or NLP, which teaches computers to read and understand human text. The SageMaker BlazingText algorithm is an incredibly fast, highly optimized tool used for text classification and sentiment analysis. You can feed it thousands of angry or happy customer reviews, and it will rapidly learn to categorize them into positive or negative buckets. BlazingText is highly tested on the exam because it is heavily optimized specifically for AWS hardware, making it significantly faster and cheaper than running open-source text algorithms on your own. Another very powerful NLP algorithm is sequence-to-sequence, which is used when your input data is a long sentence and your desired output is a completely different long sentence. The most classic, real-world example of this is language translation, where you feed the algorithm a sequence of English words and it confidently outputs a sequence of French words. It is also heavily used for automated text summarization, where it reads a massive 10-page document and intelligently generates a short, single-paragraph summary. Recognizing these specific use cases for sequence-to-sequence will easily earn you crucial points on the certification test. Now we must transition back to unsupervised learning, where we have absolutely no correct labels and must ask the algorithm to find hidden structures for us. The SageMaker K-means algorithm is the ultimate clustering tool, designed to naturally group similar data points together based solely on their mathematical characteristics. This is heavily used by marketing departments for customer segmentation, naturally discovering hidden groups of high-spending shoppers or budget-conscious buyers without any prior human guidance. The single most important exam tip for K-means is that you, the human engineer, must explicitly tell the algorithm exactly how many groups, or K, you want it to find. We briefly mentioned principal component analysis during our data engineering lesson, but you must remember that PCA is technically an unsupervised machine learning algorithm itself. It is mathematically designed to look at a massively wide dataset with thousands of columns and intelligently compress it down to just the most important, critical features. The exam will often present a tricky scenario where a complicated model is running too slowly because it has too many input features, and using PCA is the perfect algorithmic solution. Always remember that PCA reduces the physical dimensions of your data without losing the underlying mathematical story. One of the absolute most heavily tested unsupervised algorithms on the entire AWS exam is the SageMaker Random Cut Forest algorithm. Random Cut Forest is a specialized tool built specifically for anomaly detection, which means it is mathematically trained to find weird, unusual, or highly suspicious data points. You would use this incredible algorithm to monitor live website traffic and automatically sound an alarm if you suddenly receive a massive, unexpected spike in visitors that might indicate a cyber attack. Anytime an exam question asks you to detect rare events, find unusual spikes, or flag strange behavior in a dataset, Random Cut Forest is the hero you need. A very similar but highly specialized anomaly detection algorithm is SageMaker IP Insights, which focuses entirely on network security and suspicious logins. It specifically learns the normal, everyday behavior of user accounts and the exact IP addresses they typically use to access your internal systems. If an employee who normally logs in from an office in New York suddenly tries to log in from a completely unknown IP address in a different country, IP Insights flags it immediately as a high-risk event. This algorithm bridges the gap between machine learning and cybersecurity, making it a very popular trick question on the exam. While built-in algorithms are incredibly fast and easy, sometimes you need to build a highly custom, deeply complex mathematical model from scratch. For these advanced scenarios, SageMaker fully supports bringing your own custom scripts using popular open-source deep learning frameworks like TensorFlow and PyTorch. AWS provides special, pre-configured software containers that come with all the necessary deep learning libraries already installed, saving you hours of frustrating setup time. The exam wants you to know that while built-in algorithms are preferred for simplicity, SageMaker is perfectly capable of running any custom open-source framework you can possibly write. A fantastic concept frequently tested regarding deep learning is transfer learning, which is a massive time and money saver in the real world. Instead of training a giant image recognition model completely from scratch, which requires millions of images and weeks of expensive computing power, transfer learning lets you borrow a pre-trained model. You take a model that already knows how to generally recognize shapes and edges, and you just retrain the very final layer to recognize your specific business objects. The exam loves transfer learning because it proves you understand how to deliver advanced machine learning solutions while keeping AWS cloud costs incredibly low. As you face algorithmic selection questions on the exam, always follow a clear, logical mental checklist. First, determine if the data is supervised with labels or unsupervised without labels. Next, identify the exact data type, whether it is rows of numbers, thousands of images, or paragraphs of text. Finally, pinpoint the exact business goal, such as predicting a future number, classifying a category, or detecting a weird anomaly. By logically combining the data type with the final goal, the correct SageMaker algorithm will completely reveal itself to you every single time. Congratulations on conquering Section 3 and mastering the incredibly powerful art of machine learning modeling and algorithm selection. To ensure you can instantly recall all of these different algorithms and their specific use cases, I strongly encourage you to complete the attached practice test right away. Working through these scenario-based practice questions is truly the most effective way to improve your retention and prepare for the tricky technical wording of the exam. This essential practice test is completely included with this lesson, so please take full advantage of this active learning strategy right now. You are making phenomenal progress, and I will see you in the next section where we tackle model training, tuning, and rigorous evaluation. Welcome to Section 4 of our AWS Certified Machine Learning Specialty course, where we finally bring your mathematical algorithms to life through training, tuning, and rigorous evaluation. In this highly technical lesson, you will learn exactly how to teach your selected models using Amazon SageMaker, mathematically tweak their internal settings for maximum performance, and strictly evaluate whether they are actually ready for the real world. This topic is absolutely critical because deploying an untrained or poorly evaluated model can result in terrible business decisions and severe financial losses. I am thrilled to walk you through this essential phase, as this is where you officially transition from preparing data to actively creating artificial intelligence. Get ready to train your first model, and let us dive straight into the mechanics of machine learning. When you start a training job in Amazon SageMaker, it is very important to understand exactly what happens behind the scenes with your AWS infrastructure. SageMaker does not train the model on the same small server you use to write your code, because that would be incredibly slow and inefficient. Instead, SageMaker automatically spins up a brand new, highly powerful cluster of temporary training servers, copies your clean data from Amazon S3 directly onto them, and begins the heavy mathematical lifting. As soon as the algorithm finishes learning, SageMaker safely saves the final model artifact back into your S3 bucket and permanently deletes the temporary servers, ensuring you only pay for the exact minutes of computing power you actually used. Before you press the training button, you must mathematically split your beautifully cleaned dataset into 3 distinct, separate parts, known as the training set, the validation set, and the test set. You typically give the algorithm about 80% of the data to actively study and learn from, which is the training set. You use a smaller validation set, usually about 10%, to check the model's progress during the actual training phase and adjust settings on the fly. Finally, you securely lock away the remaining 10% as a blind test set, which is only used at the very end to see how the model reacts to completely unfamiliar data it has never seen before. The most common and dangerous trap you will encounter during this phase is a phenomenon called overfitting. Overfitting happens when your machine learning algorithm memorizes the training data perfectly, like a student aggressively memorizing flashcards, but completely fails to understand the underlying logic. When a model overfits, it will score an incredible 99% accuracy on the training data, but it will perform terribly on the unseen validation data. The certification exam absolutely loves testing your ability to instantly recognize overfitting by presenting a scenario where training accuracy is suspiciously high while validation accuracy is painfully low. To successfully fix an overfitted model, you must use mathematical techniques called regularization, which essentially force the algorithm to keep its mathematical formulas simple. 2 heavily tested forms of regularization are L1 and L2, which add strict mathematical penalties to the model if it tries to draw overly complex, twisted lines through your data. If you are specifically using deep learning neural networks, you can fix overfitting by using a brilliant technique called dropout, which randomly turns off small pieces of the network during training so the model cannot maliciously memorize the exact data paths. Knowing that regularization and dropout are the primary weapons against overfitting is absolutely essential for the exam. Another highly effective and commonly tested method to stop overfitting is a technique logically called early stopping. Sometimes, if you let an algorithm train for far too many hours, it will eventually stop learning broad concepts and start memorizing useless microscopic details in the data. Early stopping is an automated rule you configure in SageMaker that constantly monitors the validation accuracy during the training process. The exact moment the validation accuracy stops improving and begins to drop, early stopping immediately kills the training job, locking in the best possible version of the model before the dangerous memorization process begins. On the complete opposite end of the spectrum, you will sometimes encounter underfitting, which happens when your model is just too simple to learn anything useful at all. If an algorithm is underfitting, it will show terrible, highly inaccurate scores on both the training dataset and the validation dataset, because it simply cannot grasp the mathematical relationship in the numbers. To safely cure underfitting, you usually need to provide the algorithm with more complex engineered features, allow it to train for a longer period of time, or simply upgrade to a much more powerful algorithm like XGBoost. The exam expects you to easily diagnose underfitting by recognizing universally poor performance metrics across all your data splits. As you prepare to train your models, you must understand the critical difference between parameters and hyperparameters. Parameters are the internal mathematical rules that the algorithm learns completely on its own during the training process, without any human help. Hyperparameters, however, are the external configuration knobs and dials that you, the machine learning engineer, must manually set before the training process even begins. For example, deciding exactly how many separate decision trees to build inside an XGBoost model is a hyperparameter that you must confidently choose before hitting the start button. Guessing the perfect hyperparameters by yourself is nearly impossible, which is why you must use Amazon SageMaker automatic model tuning, also known as hyperparameter optimization. Instead of manually running dozens of training jobs with different random settings, this automated service uses a brilliant mathematical approach called Bayesian search. It intelligently runs a few initial training jobs, analyzes the final results, and mathematically calculates exactly which hyperparameters to try next to improve the score. The exam will definitely test your knowledge of automatic model tuning, specifically verifying that you know it uses prior training results to intelligently guide future guesses, saving massive amounts of time and computing money. Once your model is fully trained and tuned, you must evaluate its raw performance using strict mathematical metrics, and these metrics change completely depending on the type of algorithm you used. If you built a regression model to predict continuous numbers, like guessing the exact price of a house, you will evaluate it using a metric called root mean square error, or RMSE. RMSE calculates exactly how far off your numeric predictions are from the true, actual numbers on average. For any regression problem on the certification exam, remember that you always want the RMSE number to be as absolutely low as physically possible. However, if you built a classification model to sort data into strict categories, you cannot use RMSE, and must instead rely on a beautiful visual tool called a confusion matrix. A confusion matrix is a simple four-square grid that shows exactly where your classification model is getting things right and where it is getting wildly confused. It tracks your true positives and true negatives, which are the correct guesses, alongside your false positives and false negatives, which are the dangerous mistakes. Understanding how to read a confusion matrix is a mandatory skill for the exam, as you will frequently be asked to identify which specific type of error is costing a business the most money. From the confusion matrix, we calculate a crucial metric called precision, which measures the quality of your positive predictions. You strictly focus on precision when a false positive is incredibly dangerous or annoying to your business. For example, if you are building an automated spam filter for enterprise email, a false positive means you accidentally threw a critical, $1 million business contract into the trash folder. The exam heavily tests this concept, so whenever an exam scenario explicitly states that false alarms are unacceptable, your primary goal must be to mathematically maximize the precision score. The other side of the classification coin is a metric called recall, which strictly measures your model's ability to find every single positive instance hidden in the data. You absolutely must focus on recall when a false negative is the most dangerous possible outcome for your business. Imagine building a medical model to detect early-stage cancer in patient X-rays, where a false negative means you completely missed a deadly tumor and sent a sick patient home. When an exam question involves life or death medical screening, stopping catastrophic credit card fraud, or preventing factory machine explosions, you must always choose to maximize recall above everything else. Because precision and recall often fight against each other, mathematically improving one usually harms the other, forcing you to find a perfect middle ground using the F1 score. The F1 score is a clever mathematical formula that carefully balances both precision and recall into one single, highly readable number. It is universally considered the absolute best evaluation metric to use when you are dealing with a severely imbalanced dataset, like the rare credit card fraud examples we discussed in earlier lessons. Furthermore, you will often use an AUC-ROC curve to visually graph this trade-off, where a perfect model achieves a score of exactly 1.0, and a totally useless model scores a 0.5. When you are dealing with massive, terabyte-sized datasets or gigantic deep learning algorithms, a single training server will be painfully slow, requiring you to use distributed training. Distributed training involves linking dozens of powerful GPUs together, and you must choose between data parallelism or model parallelism. Data parallelism simply copies the exact same model onto every GPU and splits your massive dataset into small chunks for faster processing. Model parallelism, on the other hand, is used when a single deep learning algorithm is literally too physically large to fit into the memory of one GPU, forcing you to slice the actual mathematical model across multiple different graphics cards. To drastically speed up how fast your data flows from Amazon S3 into your SageMaker training instances, you must deeply understand the difference between file mode and pipe mode. By default, SageMaker uses file mode, which securely copies your entire dataset from S3 onto the training server before the mathematical learning can even begin. If you have terabytes of data, this downloading phase can waste hours of expensive computing time. Pipe mode completely solves this by streaming the data directly from S3 straight into the algorithm in real time, drastically reducing startup times and significantly lowering your final AWS bill, a highly rewarded concept on the exam. Training massive deep learning models can become incredibly expensive, but the exam expects you to know how to cut those costs by up to 90% using managed spot training. Spot instances are spare, unused AWS computers that Amazon rents out at a massive financial discount, with the catch that Amazon can suddenly take them back with only a 2-minute warning. SageMaker Managed Spot Training automatically handles this chaotic interruption for you, seamlessly pausing your machine learning job and waiting patiently until another cheap spot server becomes available to resume the math. If a certification question asks for the most cost-effective way to train a model without any strict time deadlines, spot training is undeniably the correct answer. If you bravely choose to use cheap spot instances for your lengthy training jobs, you absolutely must enable a critical safety feature called checkpointing. Checkpointing forces the SageMaker training job to constantly save its mathematical progress straight into Amazon S3 every few minutes. If Amazon suddenly reclaims your spot instance and kills the server, checkpointing guarantees that you do not lose hours of expensive mathematical calculation. When the new replacement server finally boots up, it simply downloads the latest checkpoint from S3 and resumes the training exactly where the previous server violently left off. Sometimes, despite all your careful planning, a deep learning model will completely fail to learn, and the training job becomes a massive black box of confusion. To peer inside this black box and troubleshoot broken algorithms, AWS provides an incredible tool called Amazon SageMaker Debugger. Debugger quietly monitors your training job in real time, automatically capturing millions of internal mathematical metrics and searching for common deep learning failures like vanishing gradients or exploding tensors. If an exam scenario asks how to automatically detect hardware bottlenecks or mathematical errors while a model is actively training, SageMaker Debugger is the premier diagnostic tool you must confidently select. Congratulations on dominating Section 4 and mastering the incredibly complex concepts of model training, hyperparameter tuning, and strict mathematical evaluation. To solidify your deep understanding of these highly technical metrics, I strongly encourage you to complete the attached practice test right now. Evaluating your own knowledge through practice questions significantly improves your exam readiness and perfectly mirrors the tricky evaluation scenarios you will face on test day. This vital practice test is fully included with this lesson, so please utilize it to engage in active, highly focused learning. You are truly building a professional machine learning mindset, and I will see you in the next section where we deploy your intelligent models into the real world. Welcome to Section 5 of our AWS Certified Machine Learning Specialty course, where we explore the critical phase of implementation and deployment. In this lesson, you will learn how to take your successfully trained and optimized models and safely transition them into production environments to serve real-world user predictions. This stage is incredibly important because a model cannot deliver any true business value if it remains locked inside a development notebook, and mastering deployment is highly tested on the certification exam. I am thrilled to guide you through these production-ready architectures, as this is where your data science efforts officially become live, highly scalable software applications. Let us get started and look at how AWS handles model hosting. When you want to deploy a model for real-time inference, where users need immediate predictions within milliseconds, you will create a SageMaker real-time endpoint. A real-time endpoint is a fully managed, persistent HTTPS URL that routes incoming user data straight to a dedicated virtual server running your trained model. For example, if a customer is checking out on an e-commerce website, the site sends their cart data to the real-time endpoint, and your model instantly responds with personalized product recommendations. On the certification exam, anytime a scenario specifies a requirement for low latency, immediate, individual predictions, a SageMaker real-time endpoint is the primary architecture you should select. Behind every SageMaker endpoint is a production variant, which allows you to configure exactly which model artifact and hardware type power your deployment. You can easily specify the instance type, such as a compute-optimized instance or a memory-optimized instance, based entirely on the mathematical complexity of your model. Production variants also give you the power to host completely different models behind a single endpoint URL, making it incredibly simple to test updates without changing any of your front-end application code. Understanding how production variants isolate hardware configurations and model versions is a fundamental concept for designing resilient deployment architectures. If your business does not need real-time, instant predictions and instead requires processing massive amounts of data all at once, you should use a SageMaker batch transform job. Batch transform is perfect for offline scenarios where you need to run predictions on millions of historical records overnight, such as generating monthly credit scores for bank customers. Instead of keeping a costly server running 24 hours a day, a batch transform job automatically boots up a temporary cluster of servers, processes all the files stored in an Amazon S3 bucket, saves the final predictions back to S3, and immediately shuts down. The exam heavily tests your ability to choose batch transform whenever a prompt mentions large, non-real-time datasets and a strict need to minimize idle compute costs. For businesses that host hundreds of custom, small models that are used occasionally, setting up an individual real-time endpoint for every single model becomes incredibly expensive. To solve this financial and administrative challenge, AWS provides SageMaker multi-model endpoints, which allow you to safely run thousands of models on a single shared instance cluster. When a specific user request arrives, the multi-model endpoint dynamically pulls the required model artifact from Amazon S3, loads it into memory, and serves the prediction instantly. This is a highly tested architecture on the exam, specifically recommended when you have a massive fleet of similar models with low, infrequent traffic and a strong mandate to optimize your AWS spending. A similar but slightly different service is SageMaker multi-container endpoints, which are used when you need to chain entirely different software stacks together behind a single endpoint. Imagine a scenario where an incoming raw image must first be processed by a custom Python computer vision script before being handed over to a deep learning model for final classification. Multi-container endpoints allow you to run up to 15 completely separate software containers sequentially on the same computing instance. The exam expects you to recognize that multi-container endpoints are ideal for complex inference pipelines that require multiple different programming languages or custom libraries to process a single request. If you have real-time inference needs but your incoming user traffic is completely unpredictable, with massive spikes during the day and long hours of absolute silence at night, you should utilize SageMaker serverless inference. Serverless inference completely removes the need to select or manage underlying virtual servers, as AWS automatically scales the compute power up and down instantly in response to live traffic. You only pay for the exact milliseconds of computing time used to process predictions, and your compute cost drops to absolutely zero when no requests are coming in. When an exam question describes a highly intermittent traffic pattern with long periods of idle time, serverless inference is the most cost-effective and highly rewarded architecture. Another fantastic deployment option is SageMaker asynchronous inference, which is designed for processing large request payloads that take several minutes to run, such as analyzing a massive high-resolution medical scan or a long audio recording. Unlike real-time endpoints that will quickly time out if a response takes too long, asynchronous inference places incoming requests into an internal queue powered by Amazon's Simple Queue service. It processes the request steadily in the background and can safely scale its underlying compute servers down to zero when the queue is completely empty. The exam will frequently test your ability to select asynchronous inference whenever a prompt mentions large input file sizes, long execution times, and a queue-based architecture. When it is time to upgrade an existing production model with a brand new version, you must avoid any sudden downtime that could disrupt your customers, which is why we use safe deployment strategies like blue-green deployments. In a blue-green deployment, your current live model is the blue environment, and your newly updated model is deployed onto a separate, identical green environment. SageMaker allows you to gradually shift a tiny percentage of live user traffic from the blue environment to the green environment to verify its real-world performance. If the green model performs flawlessly, you safely route 100% of traffic to it and delete the old blue environment, ensuring a completely seamless upgrade with absolutely zero customer interruption. A highly precise variant of this deployment strategy is called a canary rollout, where you deliberately route a microscopic fraction of real production traffic, perhaps just 1%, to the new model for an extended testing period. While the remaining 99% of users continue to interact safely with the proven old model, engineers closely monitor the canary model for any unexpected application errors or latency spikes. If the canary model triggers any automated alarms, SageMaker immediately rolls back all traffic to the safe older version automatically. Recognizing canary deployments as the ultimate way to minimize blast radius and strictly protect user experience during updates is a guaranteed way to secure critical points on test day. To guarantee that your real-time endpoints can easily handle sudden, massive spikes in consumer demand without crashing, you must configure automated scaling rules using Amazon SageMaker Auto-Scaling. Auto-scaling constantly tracks performance metrics like the total number of invocations per minute or the target utilization of your underlying CPU cores. If a major marketing campaign suddenly floods your website with traffic, auto-scaling will instantly spin up additional instances to share the heavy load. Conversely, when the traffic spike subsides, the system will gracefully terminate the extra servers to prevent you from wasting money on unneeded infrastructure, a classic cloud optimization practice heavily tested on the exam. Even with the best infrastructure scaling, running deep learning models on heavy production instances can become incredibly expensive, which is why AWS created SageMaker Inference Recommender. Inference Recommender is a brilliant built-in diagnostic tool that automatically loads your trained model, runs automated load tests against various AWS server types, and recommends the absolute best instance configuration for your specific workload. It provides clear, detailed charts comparing the financial cost per prediction and the total latency for each instance type. If an exam scenario asks how to scientifically determine the most optimal and cost-effective instance size for a newly trained deep learning model, Inference Recommender is the premier tool to choose. Sometimes, your business needs to deploy a machine learning model to run directly on physical edge devices that have very limited computing power, such as a smart security camera, an autonomous drone, or a factory robot. For these hardware-constrained environments, you should use SageMaker Neo to automatically optimize your model's mathematical structure. SageMaker Neo compiles your trained model down into a highly efficient binary format that can run up to twice as fast while utilizing a fraction of the memory. The exam frequently features scenarios involving edge deployment, and pairing SageMaker Neo with AWS IoT Greengrass to safely distribute the optimized model to physical devices is the ultimate architecture. When deploying custom models, you will often need to write an inference script, which is a small piece of Python code that tells the SageMaker container exactly how to handle incoming production requests. The inference script traditionally contains 4 distinct functions that SageMaker looks for, starting with the model input function, which is responsible for loading the actual model artifact from storage into memory. Next, the input function passes the incoming raw user data string, while the predict function executes the actual mathematical formula to generate a prediction. Finally, the output function formats the model response back into a clean string, like a JSON object, before delivering it to the user. It is absolutely critical to know that SageMaker endpoints can be configured to completely capture real-time production traffic for compliance and future training using a feature called SageMaker Data Capture. Data Capture allows you to automatically save a copy of every single incoming user request and every corresponding model prediction directly into a secure Amazon S3 bucket. This background data logging happens completely seamlessly without introducing any additional latency or performance delays to your active users. The exam frequently presents scenarios where data scientists need access to real-world production inputs to analyze shifting market trends, and enabling data capture is the absolute easiest way to achieve this. To secure your live endpoints from malicious internet actors and properly manage user access, you should always front your SageMaker deployments with Amazon API Gateway. API Gateway acts as a highly secure, public-facing entry point that intercepts user requests, validates security tokens, handles rate limiting to prevent denial of service attacks, and securely routes the clean traffic to your internal SageMaker endpoint. This decoupling architecture ensures that your actual machine learning infrastructure remains completely private and safely tucked away behind a robust corporate firewall. The exam loves this pattern because it perfectly aligns with AWS security best practices for enterprise application design. When your model needs to handle high-throughput, heavy computing tasks like real-time image processing, standard CPU servers might become too slow or expensive, requiring you to utilize specialized hardware accelerators. Amazon Elastic Inference was historically a common choice for attaching partial GPU acceleration to reduce costs, but modern AWS architectures heavily emphasize specialized instance families like AWS Inferentia. Inferentia chips are custom-built by Amazon specifically to deliver incredibly high throughput and ultra-low latency inference performance at a fraction of the cost of traditional graphics cards. Memorizing AWS Inferentia as the premier hardware choice for cost-optimizing heavy deep learning inference workloads will help you ace advanced infrastructure questions. As you finalize your deployment architecture, you must always remember to thoroughly test your container configurations using local mode inside your SageMaker notebook before deploying to a massive production cluster. Local mode allows you to spin up your training or inference containers directly on your small development instance using Docker, enabling you to test your Python inference scripts and verify code syntax within seconds. This completely eliminates the lengthy wait times required to provision dedicated AWS infrastructure, allowing you to debug common errors instantly. Recognizing local mode as a powerful development tool for rapid prototyping and troubleshooting is highly valued by experienced engineers and exam writers alike. In summary, mastering the diverse deployment options available in Amazon SageMaker ensures that you can handle any real-world production requirement while keeping cloud costs perfectly optimized. Whether you are building low-latency real-time endpoints for instant consumer apps, leveraging serverless inference for erratic traffic, or running massive batch transform jobs for offline data lakes, your choice must always be driven by business requirements. Always weigh the specific trade-offs between latency, compute cost, operational effort, and deployment safety to build a truly robust architecture. By maintaining a clear, logical overview of how data travels into and out of hosted models, you will confidently navigate every deployment question on the exam. Congratulations on successfully completing Section 5 and mastering the highly critical concepts of machine learning implementation and production deployment. To firmly solidify your understanding of endpoints, batch processing, and safe deployment strategies, I strongly encourage you to tackle the attached practice test right now. Working through these highly realistic scenario questions is the absolute best way to improve your retention and prepare for the specific architecture puzzles you will face on the official exam. This comprehensive practice test is completely included with this lesson, so please dive in immediately to maximize your active learning. You are doing phenomenal work, and I will see you in the absolute final section where we cover MLOps, security, and governance. Welcome to Section 6, the absolute final module of our AWS Certified Machine Learning course, where we tackle the incredibly vital topics of MLOps, security, and governance. In this lesson, you will learn how to automate your machine learning workflows, secure your sensitive data, and strictly govern your cloud environment to meet enterprise compliance standards. This topic is immensely important because creating a smart mathematical model is only half the battle, as keeping it secure, accurate, and legally compliant over time is what truly defines a professional engineer. I am so proud of how far you have come, and I am excited to guide you across the finish line as we transform your models into highly automated, secure systems. Take a deep breath, and let us dive into the world of operations and governance. Machine learning operations, universally known as MLOps, is the professional practice of applying standard software engineering principles directly to the chaotic world of machine learning. In traditional software development, engineers use automation to seamlessly build, test, and release their code into the world, a process known as continuous integration and continuous deployment, or CD. MLOps takes this exact same concept and applies it to your data pipelines, your model training scripts, and your production endpoints. On the certification exam, any scenario that demands the reduction of manual engineering tasks or the strict automation of model updates is fundamentally testing your deep understanding of MLOps. The undisputed champion of MLOps on the AWS platform is Amazon SageMaker Pipelines, a fully managed service designed specifically to automate end-to-end machine learning workflows. Instead of manually clicking buttons to start a data processing job, waiting for it to finish, and then manually starting a training job, Pipelines connects all these steps together into one seamless, automated chain. You can visually inspect the entire pipeline using the SageMaker Studio interface, making it incredibly easy to see exactly where a complex process failed or succeeded. The exam frequently tests your ability to recognize SageMaker pipelines as the premier, native tool for orchestrating complete machine learning lifecycles on AWS. As you begin automating your training processes, you will quickly generate dozens or even hundreds of different trained models, which can become an absolute nightmare to manage. To solve this organizational chaos, AWS provides the SageMaker Model Registry, which acts as a highly secure, centralized catalog for all your valuable model artifacts. Every time SageMaker Pipelines successfully trains a new model, it automatically registers it in this central vault, tracking exactly which version it is and precisely what data was used to create it. Recognizing the model registry as the central hub for model versioning and pre-deployment approval workflows is an absolute must for passing the exam. Another massive operational challenge is feature engineering, because different data science teams will often waste countless hours calculating the exact same mathematical features completely independently. To eliminate this expensive duplicated effort, you must utilize the Amazon SageMaker Feature Store, which is a centralized repository where teams can securely save and share their newly engineered features. It contains both an offline store for training massive models and a highly optimized online store for serving features instantly to live real-time endpoints. When an exam question mentions standardizing data features across an entire company or sharing calculated variables between completely different projects, SageMaker Feature Store is guaranteed to be the right answer. In the real world, the data surrounding your business is constantly changing, which means a model that is perfectly accurate today might become completely useless by next month. To combat this, you must automate the retraining of your models, ensuring they constantly learn from the absolute freshest data available in your system. You can easily configure an automated rule using Amazon Event Bridge that watches your Amazon S3 bucket, and the moment a new batch of raw data is successfully uploaded, it instantly triggers SageMaker pipelines to start a brand new training run. The exam loves testing this exact architecture, as it perfectly demonstrates how to maintain high model accuracy without requiring any manual human intervention. The fundamental reason we need continuous retraining is a dangerous phenomenon known as model drift, which occurs when the real-world environment completely changes after your model is deployed. For example, a financial model trained heavily on spending habits during a booming economy will perform terribly if a sudden recession completely changes how customers spend their money. There are two main types of drift tested on the exam, which are data drift, where the incoming raw numbers change, and concept drift, where the underlying mathematical relationship between the variables completely shifts. Identifying model drift as the primary cause of silently degrading production accuracy is a critical troubleshooting skill you must master. To automatically detect this dangerous model drift before it ruins your business, you must strictly implement Amazon SageMaker Model Monitor on all your active production endpoints. Model Monitor continuously watches the live data flowing into your endpoint and the live predictions flowing out, comparing them constantly against the original historical data used during the training phase. If the system detects a statistically significant change in the numbers, it immediately triggers a loud CloudWatch alarm, notifying your engineering team that the model is actively losing its predictive intelligence. Whenever the exam asks how to proactively discover degrading accuracy or monitor live production inputs over a long period of time, SageMaker Model Monitor is the definitive solution. Setting up Model Monitor is a straightforward two-step process that you must clearly understand for the certification exam. First, you create a baseline during the final stages of model training, which provides the monitoring system with a strict mathematical definition of what normal, healthy data actually looks like. Second, you attach a monitoring schedule to your live endpoint, configuring it to automatically wake up every hour or every day to compare the recent production traffic against that baseline. Understanding this relationship between establishing a strict training baseline and scheduling continuous production comparisons is a highly rewarded technical detail on the test. Transitioning entirely to security, you must understand that protecting your machine learning data is arguably the most critical responsibility you have as an AWS engineer. The absolute foundation of AWS security is Identity and Access Management, or IAM, which dictates exactly who and what is allowed to touch your valuable resources. You must always follow the strict principle of least privilege, meaning you only grant a SageMaker training job the exact permissions it needs to read from a specific S3 bucket, and absolutely nothing more. The exam will definitely try to trick you by offering overly permissive IAM roles, like granting full administrator access, which is an incredibly dangerous security violation you must always actively avoid. For ultimate network security, especially when handling highly sensitive medical or financial records, you must deploy all your machine learning resources completely inside an Amazon Virtual Private Cloud, or VPC. By placing your SageMaker notebook instances, training clusters, and production endpoints into private subnets, you mathematically cut them off completely from the dangerous public internet. This ensures that a malicious hacker cannot simply reach your database from the outside world, creating a perfectly isolated environment for your most secret algorithms. When an exam scenario emphasizes extreme security, strict regulatory compliance, or completely blocking internet access, utilizing a private VPC is the mandatory architectural choice. However, if your SageMaker instances are locked securely inside a private VPC with absolutely no internet access, they naturally cannot reach Amazon S3 to download the raw training data. To solve this critical networking problem safely, you must utilize AWS Private Link to create a highly secure VPC endpoint directly to Amazon S3. A VPC endpoint acts as a private, invisible tunnel that connects your locked-down network directly to S3 without ever sending a single packet of data over the public internet. This specific combination of private subnets and secure VPC endpoints is one of the most heavily tested, universally required security architectures on the entire certification exam. Network security is fantastic, but you must also mathematically protect the physical data itself using strict encryption at rest, guaranteeing that even if a hard drive is stolen, the data remains completely unreadable. AWS Key Management Service, or KMS, is the central tool you will use to generate and control the powerful cryptographic keys that lock your data. The exam requires you to know that you can easily use KMS keys to encrypt the massive datasets resting in Amazon S3, the temporary storage volumes attached to your training servers, and the final model artifacts themselves. Whenever a question mentions protecting data while it sits in storage or complying with strict enterprise data protection laws, enabling KMS encryption is the absolute right answer. You must also fiercely protect your data while it is actively moving between servers, which is known as encryption in transit. By default, Amazon SageMaker endpoints securely encrypt all incoming user predictions using standard HTTPS and TLS protocols, so data flying over the internet is automatically safe. However, when you are running a massive distributed training job, where dozens of different servers are constantly talking to each other, you must manually check a box to enable inter-node encryption. The exam will definitely test your knowledge of this specific feature, as enabling inter-node encryption can slightly increase the training time, representing a classic trade-off between maximum speed and maximum security. Enterprise companies require massive amounts of governance, which means they must have a perfect, undeniable record of exactly who did what inside the AWS account. Amazon CloudTrail is the essential AWS service that silently records every single API call made by every user, role, and automated service, creating a permanent, highly detailed audit log. If a malicious employee suddenly deletes a highly valuable production model or changes the security settings on an S3 bucket, CloudTrail will tell you exactly who did it, at what exact time, and from which specific IP address. Recognizing CloudTrail as the ultimate governance and security auditing tool is absolutely critical for any AWS certification exam. Governance in machine learning also means you must be able to completely reproduce a model exactly as it was created months or even years ago. Amazon SageMaker ML lineage tracking is a powerful background service that automatically logs the entire history of a model, documenting the exact data version, the specific algorithms used, and the precise infrastructure that trained it. If a government regulator audits your company and legally demands to know exactly how a specific AI decision was made, lineage tracking provides the undeniable mathematical proof. The exam heavily tests this concept, especially in heavily regulated industries like banking or healthcare, where extreme algorithmic transparency is completely mandatory. A massive modern challenge in artificial intelligence is ensuring your models are perfectly fair and completely free from dangerous mathematical bias. Amazon SageMaker Clarify is a revolutionary tool designed specifically to detect hidden biases in your raw training data, such as a dataset that accidentally favors one specific gender or age group over another. Furthermore, after the model is fully deployed, Clarify can mathematically explain exactly why the model made a specific prediction, completely removing the dangerous black box nature of deep learning. Whenever an exam scenario demands model explainability, algorithmic fairness, or the strict elimination of demographic bias, Amazon SageMaker Clarify is always the premier, intelligent solution. In massive enterprise organizations, you will often have dozens of entirely different AWS accounts belonging to completely different departments, which makes sharing machine learning resources highly complicated. AWS Resource Access Manager, or RAM, is the specific service that allows you to safely and securely share centralized resources, like a SageMaker feature store group, across your entire corporate organization. Instead of blindly copying massive datasets into dozens of different accounts, RAM allows all your secure departments to instantly read from one perfectly unified source of truth. The exam uses this exact scenario to test your knowledge of multi-account governance and safe organizational sharing strategies. Finally, true MLOps governance requires strict financial control, because running massive deep learning algorithms can easily cost a company hundreds of thousands of dollars if left unchecked. You must always use AWS resource tagging to heavily label every single SageMaker instance, endpoint, and training job with specific cost center codes or department names. By actively tagging your infrastructure, you can use AWS Cost Explorer to generate highly detailed financial reports, proving exactly how much money the marketing department spent on AI compared to the finance department. The exam completely expects you to know that mandatory resource tagging is the most effective administrative way to maintain strict financial governance over your cloud machine learning budget. Congratulations on completing Section 6, and a massive congratulations on successfully finishing the entire AWS Certified Machine Learning Preparation course. To firmly lock in all these vital MLOps, security, and governance concepts, it is absolutely essential that you take the attached practice test right now. Completing these highly realistic practice questions will dramatically improve your long-term retention and massively boost your confidence before you sit for the real exam. This final practice test is fully included with this lesson, so please dive in and finish strong with active learning. I am incredibly proud of your dedication, and I wish you the absolute best of luck as you earn your AWS Machine Learning certification.